Hey there, everybody. Welcome back. We're in 13.5. We're looking at the chain rule for multivariable functions. Here, we're going to take a look at how we can use it for implicit differentiation. So remember way back in Calc 1, we did this. We can treat y as a function of x, or if y is a function of x. Then the derivative of this with respect to x is 2x plus 2y times dy dx, and the derivative of the right side is 0. So we solve for dy dx, and it's negative 2x over 2y. This kind of pattern shows up a lot while we're doing this. We're going to have some negative component on the top with some positive component on the bottom. And it's related to derivatives. Let's kick this bad boy up to multi-dimension or multivariables. So we have f of xy here. And again, we're going to treat y as a function of x. So I'm showing you, this is kind of cheesy here. This is what we had before, really. We're using partials here. So the derivative of f with respect to x is equal to the partial derivative of f with respect to x times dx, which is just 1. Plus the partial derivative of f with respect to y times dy dx. And so we get rid of the dx. We can see the total derivative of f with respect to x is just the partial of f with respect to x and the partial of f with respect to y times dy dx. Did the same thing up here. We can use this idea in equations to solve for dy. Let's do that. So we're going to have f of x, y equals x to the 4th power plus y squared minus 3xy. And we'll say it equals some constant. I didn't pick a value because it doesn't really matter what the value is. But it's specifically y is a function of x. And our goal is to find dy dx. So we're going to use that formula above. We got the part, we're just following the routes. We do f with respect to x and then f with respect to y, but y has a chain rule part. So the total derivative of f with respect to x is partial of f with respect to x plus partial of f with respect to y times dy dx. Let's just evaluate it here for this problem. The partial of f with respect to x is 4x cubed minus 3y. The partial of f with respect to y, ignoring the dy dx right now, is 2y minus 3x. Note, I solved the generic form over here, just using it without plugging anything in. Dy dx equals, I subtract the partial of f with respect to x over, and which is this, and then I divide by the partial of f with respect to y. So I wrote it both ways, just so it maybe I should put a nice little box around it because it's handy. But I wouldn't memorize that one. I would memorize this one because it's related to our chain rules. Everything we've done with chain rules so far works here. Just remember dx is 1. So I'm plugging it in. If I had done it by hand, I would have 4x cubed. I'll do it right now. 4x cubed minus 3y plus 2y minus 3x dy dx equals 0. And then I move this over and then I divide by that. So that's what I'm doing here. Negative, or 4x cubed minus 3y goes to the other side. It's negative. I divide by the 2y minus 3x. And here I just distributed the negative. So that's my derivative by y with respect to x using partial derivatives in the chain rule. Okay. Let's take a look at a little bigger of an example. We'll have 3 variables here, x, y, and z. And so we'll use w. We need to write this in a form that's good for w. So I'm going to move everything to the same side. Move everything over to the left. So we'll subtract that 4xyz. So what do we need here? The partial of w with respect to x, or the partial of z with respect to x, basically. No, that's what I want. Partial of, I wrote dz dx. I want partial of w with respect to x. I have the partial of g with respect to x times dx dx, plus the partial of g with respect to y times dy dx, plus the partial of g with respect to z times dz dx. So it's dx on each of these, and then we do each of the individual components there. The partial derivatives there. Note that dx dx is 1. dy dx, y was not explicitly stated to be a function of x, so this is 0. But I wanted to show it out because this is not about formula memorization. If you know how to do the chain rule and you learn how to do it with partial derivatives, you don't need to memorize variants of this for implicit differentiation. So what do we have here? When we clean everything up, we've got partial of g with respect to x plus partial of g with respect to z times partial of z with respect to x. So if I solve for the partial of z with respect to x, I subtract that derivative of g with respect to x over, that's my top part, divide by partial of g with respect to z, that's my denominator. Since I didn't actually calculate them right here, but you can. We take the derivative of g with respect to x. I've got 3x squared, and I've got for my g of x, and then negative 4yz, that's my top part. And then my derivative g with respect to z is 3z squared and negative 4xy. So that's my denominator. That is not dz. I keep writing dz. That is dw. Nope, that was dz. I was using dw to find dz. I was right in the first place. I should trust myself. I was using dw dx, or partial of w with respect to x, to find the partial of z with respect to x. There we go. This is what we've been focusing on right here. That's what we wanted. That's what we're solving for. Damn, I kind of muddled that up a little bit. dz, or the partial of z with respect to y, is just zz. Same format. The top is just y. If you work through all this, you're going to see it's just that with y. So we got the partial of g with respect to y plus the partial of g with respect to z times the partial of z with respect to y. So we've got negative partial of g with respect to y divided by the derivative of g with respect to z. We plug in, we figure out what they are, we plug them in, and we get that. Not very exciting. It's there's a lot of parts. You just got to be careful. Don't go crazy. Just take it slowly, and you'll be fine. Peace. I got one more video. It's on polar coordinates. All right.